Welcome back to Math 320 videos. This is the final lecture for week 0 and we will be reviewing functions. First, the definition. A function consists of three things: its domain D, its range R, and the rule that assigns each an element of D to some element of R. Without specifying the assignment rule precisely, we can say f maps D to R to specify that f is a function with some unknown rule with domain D and range R. It's very important takeaway from the definition of function, and something often overlooked by students, is that a formula is not in itself a function. If you just tell me f of x is equal to x squared plus 2x plus 3, this formula is not a function. While this formula gives me the rule, it does not specify the domain nor the range, and hence we're still missing two of the three ingredients of a function. If you pair this formula with a specification of domain and range, say both being the set of real numbers, then you have specified a function. But if you pair the formula with a different specification of domain and range, say both the rational numbers, then you will have specified yet another function. Even though these two functions have the same formulaic representation of their rules, they are considered to be different functions when interpreting strictly the definition of a function. Of course, the domain and range need not coincide. We can use the same formula with the domain z and range n to give yet another different function. Notice that this function is well defined. For any integer x, x squared plus 2x plus 3 will be a positive integer that is at least 2, and hence a natural number. A further note on the notions of domain and range. In the definition, the assignment rule must be applicable to each and every element in the domain. You cannot have an element in the domain to which the rule does not apply. For example, the familiar square root function, with range being the real numbers, cannot have its domain to include the negative real numbers. In contrast, not every element in the range must appear as the output of some assignment rule. One way to think about this is to regard the domain and range as guarantees. This is something familiar to those of you who have studied computer programming in a strongly typed computer language such as Java or C, where the declaration of a function requires specifying the data types for the arguments as well as the data types of the return value. One should imagine the specific inners of the assignment rule being somewhat private, and users of the function you define can only see your declaration of what you can accept as input, the domain of your function, and what you may spit out as output, the range of your function. The strictness of the definition of the domain is so that users of your function knows that as long as an element that is in the declared domain is given to the function, it is guaranteed that the function can proceed and generate an output and not throw its hands up and say it doesn't know what to do with the element. On the other hand, by specifying a range that may contain additional unused elements, you are merely providing some engineering tolerance. A user who expects to handle a certain type of output will proceed without fail with your function so long as what the user can handle contains the range of your function as a subset. In view of this convention, we have some convenient notations. Given a function f from D to R, we write dom of f for its domain D. We write range of f, however, does not refer to the range R, but to the set of actually used output values. You can look over the set described in the set builder notation here and check that it is indeed the case. As an aside, feel free to post questions about lecture videos on Piazza. When you do so, it will be helpful to include the week number, the lecture number, and the slide number in your question, so it is easier for other students and for me to understand the context. For example, for this slide, you will want to call out week 0, lecture 3, and slide 10.4. 10.4 is the slide number shown on the bottom right near the navigation arrows. If you're not sure why the set builder notation above refers to the set of actually used output values, do ask about it on Piazza. We introduce the notation DOM mainly for convenience when having to, as we will do later in this course, refer to a bunch of different functions with differing domains. Instead of having to keep track of the mental baggage of which set in the list corresponds to which function as its domain, it is easier to just have a way to refer to the domain of this function. The ren does refer to the range of R is because one can always enlarge the range set since we do not require the range set to be exactly those elements used. In this class, it is particularly convenient since most of the functions we handle can implicitly be considered as functions with range the real numbers. And sometimes it is useful to think about precisely which values are attainable in the output. Next, we talk about function composition, which is what happens when you build a new function by sequentially applying first one function, then another. If f is a function from x to y and g from w to z, and if y, the range of f, is a subset of w, the range of the domain of g, then we can compose the two functions and get a meaningful function g composed f. The symbol to denote composition in this is this round empty circle here. The composition g composed f is the function with domain x and range z obtained by first applying the function f to an element of x, and then applying g to the resulting output. This function is meaningful since we know the range of f is a subset of the domain g, so any possible output of f can be plugged into g with no problem. Notice that in the notation, the function to apply first is written last. This is a point that frequently trips up students and is a historical oversight. Things would have made much more sense if mathematics had developed to favor the postfix or reverse Polish notation like that is used on HP scientific calculators instead of the prefix notation that won out historically. Since this is week 0 and is mostly a review, I have not prepared any exercise sheets for this week. Starting next week, there will be a separate exercise sheet corresponding to the lecture videos. For this week, I will just include this one exercise here on screen. This exercise defines for you 3 functions f, g, and h. It asks you about 4 possible compositions of pairs of functions. You are asked to decide for which of them the composition actually makes sense. And in that case, write down the domain, range, and rule of the corresponding composed function. Please pause this video and spend a few minutes to work out your response. If you are not sure about your answer, please make a post on Piazza. Next, let us review the concepts of injectivity and surjectivity. A function is injective if each element of its domain gives distinct output. Another way to think about this is that injective functions are those that can be cancelled. If you know f is injective and f of x equals f of y, then you can cancel the application of f and conclude that x equals y. Important, this cannot be done for general functions, only injective ones. To prove a function is injective, you have to prove either that if x and y are distinct elements in the domain, then their outputs f of x and f of y are different. Or the contrapositive statement that if f of x and f of y happen to be equal, then x must equal y. This is something I hope you remember having some experience with in Math 299. I will sometimes use the word injection to refer a function that is injective. So instead of saying f is an injective function from x to y, I may say f is an injection from x to y. A function is surjective if every element in the declared range is used by the rule. Notice that the definition is only operative because we allowed the range of the function to be bigger to contain elements that are not used by the function's rule. Another way to think about surjective functions is that they are those which can be solved. The equation f of x equals y always has a solution for any y in a declared range. Note that there could be more than one solution in general. I will sometimes use the word surjection to refer to a function that is surjective. Coming back to an earlier theme, that functions are not just formulae. Whether a function is injective or whether it is surjective depend on the choice of domain and range. This is something you have actually already encountered in Calculus 2 when you studied inverse functions. There are several web work questions for Math 133 that ask you to find a domain on which a given formula makes an invertible function. To illustrate this notation again, let's start with the formula f of x equals x squared plus 1. If we think of this formula as that of a function from R to R, this is neither injective nor surjective. If we think of this formula as that of a function from N to Z, it is injective but not surjective. If we think of it as a function from R to the set of real numbers greater than or equal to 1, then it is surjective but not injective. I encourage you to pause the video for a few seconds and verify that these three statements are in fact true. Finally, another new vocab word. A function is bijective if it is both surjective and injective. I will also use the word bijection as short for bijective function. In Calculus 2, you are treated to a different word for this concept, the word one-to-one. A bijective function is precisely one that can be inverted. Remember, an inverse function is a function that swaps the domain and range and reverses the assignment rule. That's it for this lecture. Again, at the end, here is a table of new LaTeX symbol used. See you next time.